this. Is this better?
Cool.
Yes.
So good.
That's good.
Yeah, sorry for the interruption.
Thanks for letting me know. Yes. So I was introducing what zkSNARKs are, and the setting we have is that we have prover and verifier, and the prover sends a proof to the verifier. Now this proof, we want it to be short, which means it is shorter than the witness, and we want the verifier to verify the proof more quickly than it can check the witness. And zkSNARKs, we require them to satisfy two security properties. First is knowledge and soundness, where it states that if the verifier accepts, then the prover must have known a witness. And secondly, we have zero knowledge, which means that the proof hides the witness. Now, zkSNARKs have found a lot of applications in blockchains. So we have many companies that are all working in this blockchain space, utilizing zkSNARKs in order to solve problems in both privacy and scalability, such as with private smart contracts, private transactions, and zk rollups. zkSNARKs have also found other applications, such as proof of solvency for exchanges, certifying image provenance. There's been a series of work recently, and also for content moderation. So, as zkSNARKs are getting deployed in practice, it is crucial to understand whether they can withstand all attacks that are possible in practice. And it turns out there are two classes of attack which are not captured by the standard zkSNARK security measure. The first are adaptive attacks. In these attacks, we have the prover that can compute the statements and the proofs simultaneously. And thereby, it may be possible to make the verifier accept a statement that is false or accept a statement for which it doesn't know the witness. Secondly, we have malleability attacks. In these attacks, the prover may modify a valid proof to a new proof without necessarily knowing the witness. These properties are not ruled out by either non-adaptive knowledge soundness or by zero knowledge. And in fact, we've seen some attacks in practice for adaptive attacks, insecure instantiations of the Partition transform, which I'll talk about later, have shown to attacks against the Helios splitting systems, and so on. Malleability attacks have also been problems in Bitcoin transactions. Our takeaway here is that we need stronger security properties for deploying zkSNARKs. Now, one such strong security property is called simulation-extractability. And informally, it states that knowledge soundness still holds even when the malicious prover gets some extra power. And this extra power has to do with it's being able to get simulated proofs of arbitrary statements, even possibly false. So here in this experiment, we have a simulator that can generate simulated proofs, and the malicious prover can query the simulator for whichever statement it wants. And even with this extra power, and even with the power of adaptivity, which means it can sense the statement at the same time as the proof, the knowledge soundness still holds, which means if B accepts, then P must have known a witness. From this sort of informal definition, we can sort of see how this would rule out the previous two classes of attacks, namely adaptive and malleability attacks. Moreover, turns out that in many proposals of private smart contract platforms, SIM-EXT is a required property in order to prove the system secure. So given the role of SIM-EXT in real world security, one might ask, which zkSNARKs satisfy SIM-EXT, and can we build them? Prior works have shown that we can either build zkSNARKs that satisfy SIM-EXT from scratch, or they can achieve SIM-EXT via generic transformations. But recently, people have shown that certain zkSNARKs satisfy SIM-EXT out of the box and without any modification. These results were shown for the proof systems Sonic, Dr. Marlin, and Bulletproofs. Now, these works either deal with SNARKs that are not so-called transparent, which means that they need some sort of trust setup with some trapdoor that must be dealt with, or in the case of Bulletproofs, which is transparent, meaning there's no trapdoors, they require a property, they require working in the algebraic group model, which morally should be a stronger than necessary assumptions. We only expect Bulletproofs to satisfy security, assuming just discrete log and the random oracle. Now, with these in mind, our central question in this work is to answer, can we show that transparent zkSNARKs satisfy SIM-EXT under the same assumptions that we used to prove their soundness? And we show this for two systems, Spartan and Bulletproofs. We choose these two proof systems because they are, in some sense, state-of-the-art, or they have been deployed in real systems. And also, as I mentioned, the assumptions that we base our proofs on are discrete log and the random oracle model. These are minimal in order to prove that these proof systems are secure or just sound in general. To prove our results, we developed a few tools that might be of some independent interest. One, we show that there's a template for proving SIM-EXT from solid properties, and we show how to instantiate this template for Spartan and Bulletproof. Secondly, we prove a more general tree extraction lemma. This is used in the course of proving knowledge and soundness. These are built on very recent ones.
So will the zero knowledge property be affected by, for example, malleable attack?
Yeah, I don't think it is.
So it's fine.
With
Yeah.
simulation extraction? Yeah, simulation extraction keeps zero knowledge.
Yeah, it keeps zero knowledge. So I guess it is possible for proof systems not to be zero knowledge, but also is non-malleable. However, in this work, we start with the zero knowledge proof systems and then show that it is non-malleable.
Wait, what's the question? Is malleability dangerous for zk, right? Isn't that what?
Yeah,
Like,
yeah.
in the case that if I can maul the proof, can I somehow break zk? It's possible that in a bigger system, sure, right? Like, presumably I could observe behavior based on some maul proof or something like this. But
Yeah, I guess like
normally there's no connection, right?
yeah, I think in a standalone definition, there isn't a clear connection between malleability and zero knowledge.
In simulation extraction, for other definitions of non-malleability, I agree, but for simulation extraction, it bakes simulation directly into the proof.
Yes, that's right. Yeah. So yeah, simulation extractability is something that is strictly strictly stronger than non-malleability, because it also assumes that the proof system satisfies zero knowledge. Okay. Any other questions? So let's move on to the agenda for the rest of the talk. First, I will talk about a general template for proving the SIM-EXT property. Second, I'll talk about how we instantiate this template for Spartan and Bulletproofs. And finally, I'll talk about our tree extraction. So to start, let me recall the Piaget transform, which is used by many zkSNARKs, including Spartan and Bulletproofs. And it goes as follows. First, you construct an interactive and public Quang argument. This means that the prover and verifier may interact over a number of rounds. And the verifier's messages or its challenges are uniformly random. And then we transform this interactive public Quang argument into a zkSNARK via Piaget, where both parties now have access to a random oracle. The prover would compute all of the messages in advance and sends it all in one go. And the challenges are derived from hashing using the random oracle on each of the prefix of them. So next, let's revisit the definition of simulation extractability. Here we have a potentially malicious prover and a verifier. They both have access to the random oracle, and the prover also has access to a proof simulation oracle. Now, this prover can query it on arbitrary statements that it likes, and it gets back simulated proofs. And the Q will be the sets of all simulated proofs. Now, when the prover sends a statement in proof to the verifier, what SIM-EXT says is that there exists an extractor such that if B accepts and this is not a simulated proof, then there exists a witness, then the extractor can extract out a witness that satisfies the relation, a satisfying witness for the statement. So the SIM-EXT definition is somewhat complicated, but we do know the knowledge soundness definition, which essentially just removes the proof simulation oracle from the SIM-EXT scheme. So knowledge soundness is a simpler notion, and people have known how to prove it. The question now is, can we reduce SIM-EXT to knowledge soundness? So one difficulty here when we try to reduce this is the fact that in this proof simulation oracle, it can actually reprogram the random oracle in order to produce simulated proofs.
So in the SIM-EXT, you have it if x comma pi is not in Q, where Q is this set from the simulation interactive. Does it not say anything about if x and pi is in Q?
Yeah, it doesn't say anything because this is a trivial way to make the verifier accept, right? Like you ask for simulated proofs and you send the same proof. Okay.
What is the order to get access to the random oracle? What is that allowed to do?
Yeah, it's because usually when you apply Piaget, then your simulator must program the random oracle in something. I have not seen any proof systems where you can simulate without program the random oracle.
Back to for most proof systems or the theorem. A non-programmable random oracle is not enough. I think it's like the Benson case 16 paper.
Yeah, because like if the simulator cannot program the random oracle, then morally it has the same power as the prover.
Right.
Right. So it shouldn't happen. Okay, so let's try to reduce SIM-EXT to knowledge. So our strategy is that on the left, we have the SIM-EXT malicious prover. On the right, we have the verifier. And in the middle, we want to construct some adversary against knowledge soundness. And the strategy to emulate a knowledge soundness adversary goes as follows. It will have simulate the view for the SIM-EXT malicious prover. So to do that, it has to deal with the reprogramming of the random oracle. Okay, so let's instantiate some local table. So once we have this table, we can simulate this proof simulation oracle, and it keeps all the program queries within this local table. Now, let me just remind you quickly, usually how these simulators work. And what they do is they sample random challenges first. They compute the proof based on these random challenges. And finally, they reprogram for each of the proof prefix to be equal to the challenges that it has chosen in step one. Okay. So now the SIM-EXT prover, when it wants to ask some random oracle queries, we now have two cases. Either it is a programmed query, in which case it will be answered from this table T, or it will be answered by the knowledge soundness adversary's own random oracle. And finally, once the SIM-EXT prover sends a proof and statement pair, it would pass it on if this proof is not simulated. So this is a strategy to simulate the view of the SIM-EXT prover, and the end goal is to get a knowledge soundness adversary. Now, if the simulation is successful, then we can invoke the knowledge soundness extractor in order to get a satisfying witness depth. So recall here that if we assume knowledge soundness, then there exists such an extractor, and we're just invoking such an extractor. The problem with this approach is that we have this local table of programmed queries, and that might lead to inconsistency in the verifier's view of the random oracle.
So is this because the knowledge soundness prover can internally reprogram its simulated oracle but can't touch the actual random oracle?
Yes, exactly. So let's think about this problem in more detail. Okay, what is the verifier's view of the random oracle? So it will verify by querying the random oracle at these specific places, right, in order to derive the challenge. Now, when does this view differ? It differs if a prefix of a simulated proof will coincide with the corresponding prefix of the proof that is sent at the end. So when this happens, the proof will be verified, like it would be verified with respect to the result from the random oracle. This is going to be different from the result of the program. And therefore, we have an inconsistent view. Our goal is to bound the probability that this happens. Let's call this a bad event. So let's try to define this bad event. What happens in this bad event is that the simulation oracle outputs a proof type prime such that it coincides with the proof pi at some prefix. Equivalently, let's think of this as you have this knowledge soundness adversary, and it is able to produce two different accepting proofs, pi and pi prime. They are different, and yet they have the same prefix up to some point. And also, because this is output by a simulation oracle, let's also graph this guy the power to program the challenges. Now, given this bad event, turns out that this is too strong. There is a very easy counterexample that makes this always happen. The counterexample goes as follows. So assume we have this interactive proof systems that has, say, 3 rounds. And the first and the second round message from the prover are randomized. This means that when the prover tries to generate the proof honestly, it can have some randomness in both the first round and the second round. So let's consider this and consider what happens when you apply Piaget to this. Then you can use a valid witness in order to generate 2 accepting proofs that differ in the second component onwards, and yet they're the same in the first component. The way to do that is assume you're in the mind of the proof, right? You just try to generate 2 honest proofs. But in the second round, because the message is randomized, you can just create 2 different second round messages. And that leads to sort of trivially breaking this bad event.
Wait, how does this work in the Piaget mirror?
Yeah, Piaget mirror, you just you compute A1, you query the random oracle for C1,
Right.
you compute A2, you query for C2, and so on.
Yeah, I know, but
Yeah.
in the Piaget mirror, how can it create 2 different proofs?
Yeah, so it creates the same A1,
Uh,
right? And then for A2, because it can produce A2 with some randomness,
Oh,
it just chooses different randomness for A2. And that leads to A2 and A2 prime that difference.
I see.
So how do we fix this bad event? The idea is we want to restrict the random oracle programming to a much smaller set, and particularly to only a single round. What I mean by this is that I'll define the following 2 definitions. First, there's K0 knowledge, where there exists a simulator, I'll call this SIM-K, that can reprogram the random oracle only in the Kth round. So what this means is that this is the usual simulator, and this is the KZK simulator. It can only reprogram in the Kth round instead of in all the rounds. And we want the resulting simulated proofs to be close. Secondly, we have a notion called K-unique response. This means that an adversary cannot produce 2 different accepting proofs that agree up to round K with an extra power to program the Kth challenge. So even if it can choose the challenge for the Kth round, it is still not possible to make I and I prime agree up to round K and then diverge afterwards. This is what is roughly meant by unique response, meaning it cannot continue the proof after round K in 2 different ways. Okay. So with these 2 notions now defined, I will state the theorem in a previous work that shows SIM-EXT is exactly equal to having knowledge soundness plus having KZK and KUR for the same round K.
So this is for any K, right?
This is, yeah,
Okay, so if you can find your underlying scheme to satisfy for any K, like for example, K1
Yeah.
or 2.
yes. Usually there's only one choice of K that works.
Oh, okay.
Also, why do you care about giving P-star this additional power to reprogram the K?
Yeah, so it has to do with sort of faithfully sticking to the SIM-EXT experiments. And remember that in the SIM-EXT experiments, the prover may, like, the knowledge soundness adversary may generate simulated proofs. And these simulated proofs, they are allowed to program the case challenge. That's where it's coming from.
Just to make certain I'm understanding the statement correctly, this is bidirectional and only applies to non-interactive server, right?
Yeah.
Okay.
Yes, because these sort of have the random oracle baked in.
Right, yeah.
I'm not sure what
wondering
is that. In the standard model, I don't know what this analog theorem is.
Right, yeah.
Okay, so let me just also give a quick overview of how this proof goes. And it goes by basically a series of hybrids. First hybrids, you switch the normal simulator to the KZK simulator. And this is indistinguishable from the original SIM-EXT game because of the KZK property, right, which states that the KZK simulator is a balanced simulator. In the second hybrid, we now have our bad event, where this means there exists a simulated proof that has the same K prefix as time. And here we appeal to the KUR notion. We show that these two hybrids are the same up to bad. And when this bad happens, we can build a KUR episode. And finally, we can show that once we condition on that not happening, then we can perfectly simulate the SIM-EXT adversary by the knowledge soundness adversary. And thereby we reduce the knowledge soundness gain. So let me continue to the second part of my talk, where I'll show how to instantiate this template for Spartan and Bulletproofs. So first, I'll talk about Bulletproofs. In particular, I'll talk about its range proof protocol. They also have sort of an arithmetic.
Sorry, Quang.
Yeah.
We have one question in the chat.
You-
You still have to use some type of working lemma for this? Like for the previous slide?
Yes, definitely.
Mhm.
The forking lemma is used to prove knowledge soundness. And what I showed before is that we can reduce the SIM-EXT to knowledge soundness under these two extra assumptions, extra properties. Yeah. So in this range proof, we have a Pearson commitment to the value v, and v is in this specified range. And we want to prove the statement where the commitment is public and the value and the randomness is private. Now, the range proof proceeds as follows. First, the prover will send a commitment to v and a commitment to some extra randomness row. Then you get some challenge. Secondly, it will commit to some so-called cross terms that I don't have time to write in full here. And third, it will send sort of the evaluations at this challenge point. Once all that is done, we have an inner product argument that basically shows that some value is equal to the inner product of two witnesses.
So what are these cross terms intuitively?
Yeah, so it's sort of like when you try to multiply two polynomials and you care only about one coefficient of that. So you send the commitment to all the other coefficients of the polynomial. So it accepts the inner product arguments accepts, and the evaluations are correct. So recall, we need to show these three properties. And right now, I'm just going to focus on showing the second two. The latter two. Now the question is, we can choose the round K to prove KZK and KUR, right? And the overall heuristic I'm going to use is that we choose the last round where the honest prover can use randomness. And this last round is going to be round 2. Because in the first 2 rounds, the prover can sense commitments, and commitments are inherently randomized. But after that, there is no more randomness. Okay. So let's try to prove 2zk. Here, it means that the simulator can only reprogram the challenge X. Now, the idea to get such a simulator is that first, we try to commit to a random witness, B prime. Now, this random witness will probably not be satisfying, but we just keep continuing. Then we skip the second round messages and we choose the third round message. And then we go back and we choose the second round messages to be consistent with the third round. We can choose messages out of order this way because we have the opportunity to reprogram the random oracle. And finally, because we chose the random witness B prime and row, we actually have valid witness for the inner product arguments, and we just execute that honestly. And that is going to be our simulator. So now let me try to prove 2 unique response. And also recall that you want to show you cannot output 2 different proofs that agree for the first 2 rounds and diverge for the rest. Even if you can choose the challenge X. So let's say it diverges like this. Then the first idea is, here's this inner product argument. Why don't we just extract out the underlying witness? Just to make our job easier. So now we can assume that the prover sends in the third round also these witnesses because we have extracted them. Next, we will show that if the third round evaluations are different, then we have a non-trivial discrete log relation. This follows because here is the evaluation check equations. And what's interesting about this is that we have this G and H to the power of T hat and beta X, right? These are the third round evaluations. And they're both equal to something that is fixed after the first 2 rounds. So the middle term here, you can see that once you fix X, even if the prover can choose any X that it likes, once you fix X, this quantity is fixed. And thereby we have a non-trivial discrete log relation. Next up, similarly, if the 2 underlying witnesses are different, then we also get a discrete log relation. And finally, once everything is the same, especially these witnesses, we argue that the proof are the same as well. Like the inner product arguments are the same. And that leads to a contradiction because we cannot have 2 different proofs. So
Sorry, can you go back to the last?
yeah, exactly.
So here, like, it seems like you only need to reprogram like 1 round, but like, from my intuition, bulletproofs is like recursive for many rounds, right? So how is just reprogramming 1 round like, why is it sufficient?
Yeah, so this programming, is it about the like to prove the simulator, right? So let me go back to that slide. Yeah. So the reason it can only reprogram that is because we don't need to reprogram during the inner product. That is because we have executed this with valid witnesses. So we can use the honest prover's algorithm to compute these.
Oh, I see. So there's only like the layer on top of your product argument that you're like.
Yeah,
Ah, I see. Okay.
yeah, great question. So, I will continue talking about, Spartan, if nobody else has any other questions. Okay, so Spartan is a different proof systems. It is still based on discrete log, but the relation is different for one. This is something called right one constraint system, and it is an NP-complete constraint. Here we have the matrices A, B, and C, and the public inputs X, which you can think of as like the structure of the circuit and the public input in the circuit. And then you also have this witness W. And Spartan proceeds in more rounds than bulletproofs. Essentially, first the prover commits to the witness, and then it does a bunch of subprotocols. In particular, it does the first version of the subject protocol. Then it does something called a product check, and then another subject. It will open this witness to some evaluation point, and finally it does an equality check. So we have all these subprotocols, and the verifier accepts if all these subprotocols all accept. So given this, we can ask the same as bulletproofs, which round K has the last randomness, and then we'll try to prove KZK and KUR based on this round K. Turns out it is the last round, or the next to last round of this equality check. Let me try to prove KUR first, where K is this last round N. And the main observation here is that quality check is just a simple signal protocol. Let me give this signal protocol. It is a free message protocol of this form. And what do we want here? Right? We want to make it impossible to have two different Z's that can make the proof accept. This is the case because based on this verification equation, Z is uniquely defined given any challenge C. So KUR is relatively easy to prove here. KZK, on the other hand, is a bit more challenging. And the main problem is that how do we simulate all the prior subprotocols if all we can do is reprogram one challenge in the last equality check? Now here the idea is somewhat similar to bulletproofs, which means that we try to generate real proofs, honestly generate proofs with witnesses for all of the prior subprotocols. So at first, we commit to some fake witness W, which is not going to be satisfiable, but we try to keep it going with this W. And it turns out you can do precisely that. You can just try to make the first subject protocol accept, and then make the product check with the second subject and the opening arguments, they all accept. And finally, you push this contradiction into the final equality check. And there, you can simulate this, because the simulator works even for false statements. So,
So can you go back one
yeah,
second?
definitely.
Yeah, so I just find it really cool that you could push the contradiction all the way back to the last check. Do you know if it's like something that's very specific to Spartan, or do you feel like just general subject based protocols can support this?
I think it's somewhat of a general theme. Like I've seen some other proof systems and they also can do this. I don't know of a good way to abstract out this property. So if you can think of like that, that would be awesome. So lastly, I'm going to show our tree extraction theorem and how it is used to prove knowledge soundness. So a closely related notion to knowledge soundness is special soundness. And what it says is that here is the proof systems, and we try to build a tree of transcripts. This tree of transcripts has the following form. First, it proceeds from the first prover's message, and then it branches out with K1 different challenges. Then it keeps branching out. The second layer has K2 children, and so on. So final layer has Kn. Special soundness says that, and also all these proof, once you travel from root to leaf, they form an accepting proof. Now, special soundness says there exists some arities K1 to Kn such that we can always extract a witness from any such tree of accepting transference. And so I'm going to denote this extraction process by some tree extractor. So this is good if we know how to produce such trees. But how exactly do we do that? Here, a prior result due to Attema et al. Comes into play. What they say is they construct this tree builder that can build a K1 to Kn tree of accepting transcripts, where K1 to Kn can be arbitrary values. And they can do this in expected polytime. The time here is basically the product of all these Ks, so the tree size times the number of random oracle queries of the adversary. And this algorithm is actually quite simple. You just try to reprogram the random oracle to different challenge points in order to branch in the tree, and it keeps doing that. The challenging aspects of this is to analyze this algorithm and then show that it terminates in expected polytime. So given this lemma, we now can see that special soundness implies knowledgeness. And this is because first you use the tree builder to build the tree, and then you use the tree extractor to extract the witness. So far, so good. It turns out that Spartan and Bulletproofs do not satisfy special soundness as I defined it. Instead, it satisfies some generalized notion. This notion differs in two ways. First way is that this tree of transcripts needs to have satisfy some extra predicates on the set of challenges at each level or at certain levels. So for example, in the first level, we may want the challenges to satisfy some predicates. Secondly, we want this tree extraction process to have some chance of failure, but when it fails, you can break some computational assumptions, such as discrete-log. So the second change is easy to incorporate into the special soundness framework. Basically, you just have an extra term where you bound this advantage by the advantage of breaking discrete-log. But the first notion is a bit more difficult. So how do we build the tree with extra predicates? And what are the extra predicates that we care about? So what we did is we show a generalized tree builder that can work on what is called partition predicates. And it basically says you have some partition of the challenge space into different sets, and you want the challenges to lie in different sets. This is something that is quite elementary, and it captures what is needed for bulletproofs and Spartan. Namely, for bulletproofs, you want the challenges to be not equal to plus or minus of each other. And this corresponds to the partition where you just partition into sets of x and minus x. Secondly, we have Spartan, where at one point there are two challenges sent back in a single round, and we have to rewind this once. And then we want these two tuples to be linearly independent. And these corresponds to partitioning the set of challenges into different lines. Yeah, and let me also mention this AFK contributor from the work of Attema et al. They just handle what is called the distinctness predicates, which means that they just care that the challenges are different. This corresponds to a partition where you set every partition to be a singleton set. So the idea to prove this generalized tree building theorem is quite simple. What we do is we try to reduce this partition predicate into a distinctness predicate, and then we apply the AFK contributor. So first, to reduce this, we just pick a random representative from each of these partitions. So imagine this is your partitions. You pick a random representative, and this will be sort of the new oracle, the restricted oracle, that we're going to apply this AFK contributor upon. So both the malicious prover and the contributor will have access only to this restricted random oracle. And the overall idea is that since this AFK contributor guarantees distinctness of these challenges, it will go back and corresponds to the challenges being in different partitions. And that is the end of the proof.
So how do you ensure that the resulting challenge space is like large enough and random enough? Because this kind of depends on how you pick your partitions, right?
Yeah, it does. So like example in Spartan and Bulletproofs, the partitions we choose are sort of very equal.
So like for every new partition, you have to like write a proof that the resulting links it.
Yeah, I mean, there's going to be a term that depends on the partition. Like if the partition is unbalanced, then you get a greater loss from the theorem.
And this is only dependent on the size of the partitions and number of partitions or the other factors. Right?
Yeah, just the size and the number. So that is going to conclude the main part of the talk. And now let me make a summary. So in this talk, I showed that bulletproofs and Spartans, they are two transparent zkSNARKs, and they satisfy SIM-EXT, which is a strong security notions that seems to be sufficient for ruling out most attacks in practice. We do have an important limitation of our work, and it is because we use rewinding in proving knowledge soundness, we incur a non-time trap. This seems to be somewhat inherent to the use of rewinding, but we hope that this can be improved in later works. So in terms of future work, we would like to prove SIM-EXT for more general classes of protocols and not just one proof systems at a time. So such classes of proof systems may include something like polynomial IOPs or for recursive stuff. As I mentioned, it would be better to have a tighter rewinding bounds, in which case we could say more about the practical bit security of these systems. And finally, there's an even stronger notion that SIM-EXT holds UC security, and we wonder if this proof system can be shown to satisfy this strong notion. So, this is the end of my talk. Feel free to read our paper. Thank you.
To make the SNARK satisfy UC security, the simulator would have to be able to extract a witness without rewinding, right?
Yeah, so the challenge with UC security, which is sort of a concurrence notion, is that the extractor needs to extract without rewinding, and the simulator needs to simulate without programming. This seems like very strong and not possible with this current approach.
Yeah, so it seems like maybe the strongest you could hope for is proof size that goes with like the witness size. Because then you could like carry around an encrypted witness or something.
Yeah. Yeah,
And do the simulator draft word of that, but like, do you think there's any hope for breaking that down and getting UC proofs where the proof size is actually smaller than the witness size?
yeah, so there's a recent work in Eurocrypt this year, I think, that shows if you additionally assumes the algebraic group model, then you can get witness succinct UC size.
What's this paper called?
Yeah, I think it's witness succinct universally composable size.
Okay.
But so what that means is that it's as big as the witness, right?
No, it's like, yeah, I'm not too sure. My impression is that they can even reduce the size of the witness. Like the proof size is going to be shorter than the witness size. Yeah, and they do that using some fancy tricks. Yeah.
Also, Rhea, I think you can use something like efficient transformation to like induce like sort of proof work for the prover, and then you can still get like a same proof. But still having this discrete-log-based. Because essentially how it works is you just force the prover to make a bunch of normal inquiries, which they extract.
Right, and then the extractor can sort of figure out what must have happened.
Yeah, exactly.
I see, but so I see, so it's yeah, Shamir plus makes you see the succinctness.
Yeah, right. I think there's some, yeah, okay.
I see, yeah. I mean, the breakdown extractor sort of does almost that. But yeah, also.
We have one more question in the chat. Do you prove SIM-EXT also for the version of Spartan with a trusted setup instead of transparent? Trusted setup Spartan uses a variant of the KZG commitment for multilinear polynomials.
Yeah. So about the sort of generalizability of our proof. So let me try to go back here to the Spartan slides. So recall that we showed SIM-EXT to be established if we can establish these smaller properties, right? Knowledge soundness, KZK, and KUR. Now, the only parts that needs to be switched out in such a proof when you use a different polynomial commitment is the knowledge soundness. Because as far as I know, our proof of KZK and KUR does not really use the choice of the polynomial commitments. That makes sense.
I still have a question about like the tree, those additional predicates seem dissatisfied. So there's a second point there, and I didn't quite understand what the intuition for having the second point was.
Oh, oops. You mean this slide or the?
I think it might have been the next slide, actually. Yeah, the next
Yeah.
slide.
Oh, yes, like this,
Yeah.
when it fails, you break some computational assumptions,
Mhm.
right? Yeah, I mean, it's just something that we have to deal with. Because in the course of extracting from, say, a bulletproofs inner product argument, it may be the case that we run into this issue. Like,
I see, but you want to do this at tree builder level and not the.
yeah, so this we can do it as at the tree extractor level. Like the tree extractor gets the tree, and either it outputs a witness or it outputs discrete log relation.
Okay, so it is a tree, it's like, okay, so it is a tree.
Yeah.
I guess if there are no other questions, thank the speaker again.